Okay, so today we're going to be talking about our first topic in the unit of gravitation. And this won't be on the AP test, but I think it's not only really important to learn, but a good review of some of the other topics that you've studied. So, universal gravitation and circular orbits. And we'll start with John F. Kennedy, President John F. Kennedy, talking about landing a man on the moon.
These are extraordinary times, and we face an extraordinary challenge. Our strength, as well as our convictions, have imposed upon this nation the role of leader in freedom's cause. Now going on around the world between freedom and tyranny, the dramatic achievements in space which occurred in recent weeks should have made clear to us all, as did the Sputnik in 1957, the impact of this adventure on the minds of men everywhere who are attempting to make a determination of which road they should take. Since early in my term, our efforts in space have been under review. With the advice of the Vice President, who is Chairman of the National Space Council, we have examined where we are strong and where we are not, where we may succeed and where we may not. Now it is time to take longer strides, time for a great new American enterprise, time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth. I believe we possess all the resources and talents necessary, but the facts of the matter are that we have never made the national decisions or marshaled the national resources required for such leadership. We have never specified long-range goals on an urgent time schedule or managed our resources and our time so as to ensure their fulfillment. I therefore ask the Congress, above and beyond the increases I have earlier requested for space activities, to provide the funds which are needed to meet the following national goals. First, I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. In conclusion, let me emphasize one point. It is not a pleasure for any president of the United States, as I'm sure it was not a pleasure for my predecessor, to come before the Congress and ask for new appropriations which place burdens on our people. I came to this conclusion with some reluctance. But in my judgment, this is a most serious time in the life of our country and in the life of freedom around the globe. And it is the obligation, I believe, of the President of the United States to at least make his recommendations to the members of the Congress so that they can reach their own conclusions with that judgment before them. You must decide yourselves as I have decided. And I am confident that whether you finally decide in the way that I have decided or not, that your judgment, as my judgment, is reached on what is in the best interest of our country.
Okay, so the physics that made us confident that we could figure out how to get to the moon and back is based in Newton's universal law of gravitation, knowing that masses attract other masses. And that equation is the force of gravity, Fg, which you're familiar with, is equal to this constant, which is a very small number, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That should be to the power of negative 11, times the first mass times the second mass in kilograms, all standard units, divided by the radius squared in meters. And this is a 1 over r squared law. There are lots of several 1 over r squared laws in physics. electric force is a 1 over r squared law. Magnetic force is often a 1 over r squared law. Light intensity is a 1 over r squared law. And this is the first one you guys have seen in this class, but it's a common format. And if the object has Fg on the surface of the Earth, where the m is the mass of an object attracted by the Earth, then one of the m's cancels out there, and it becomes little g equals g m mass of the Earth over radius squared. I did that little derivation, and you can see that if you put in the numbers for the mass of the Earth and the radius of the Earth, you get little g equals 9.8, as you would expect. Okay, so try using the formula to calculate the gravitational force between two objects, in this case 2 people, of mass 50 kilograms if they're standing 2 meters apart, and then pause the video while you do that. It's a pretty straightforward problem, and you can see that the force of gravity between 2 people is so small. It's much smaller than electrical forces between the electrons on the surface of your atoms. You'd never feel this force, 4 times 10 to the negative 8 newtons. Okay, so this is an illustration from Newton's book, the Principia Mathematica, and he had this thought experiment where he said that, say there was a big mountain on Earth, and you launched a cannon. In those times they had cannons. Launched a cannonball at a certain speed, it would go a certain distance. And if you launched it faster, it would go a further distance. And if you launch it faster, so this is projectile motion, right? But as you start to take into account the curvature of the Earth, you can see that it's going to follow the curvature of the Earth until eventually it falls. But if you make the cannonball go just fast enough, it will continue to fall, and it will never actually reach the Earth. It will just keep falling and missing the Earth. So a few questions for you to consider, and I'd like you to think about these and pause the video. If the cannonball is traveling fast enough to stay in orbit, is it still falling? What is the most important factor for a satellite to stay in orbit? Because, of course, the technology today that looks just like this cannonball is satellites. And why do astronauts experience a feeling of weightlessness when they're in the space station, which is a satellite orbiting the Earth? Okay, think about those and pause your video. Okay, here's a reading from Physics for Future Presidents by Richard Muller. He's a professor at UC Berkeley, about satellites. The velocity required to stay in orbit depends on the altitude, because the gravity of the Earth gets weaker at higher altitudes. The Earth is large, so the effect is small until you get very high. At 100 miles altitude, gravity is 95% as strong as it is on the surface. The reason astronauts feel weightless is not that gravity isn't there, but that they are falling. So there's the answer to one of your questions. At 200 miles altitude, gravity is 90% as strong. That means that the velocity required to orbit is slightly less, by about 5%. Rocket scientists need to know about that decrease, but the important factor for future presidents is that all low Earth orbits, LEOs, require speeds of about 5 miles per second. At that speed, the satellite goes around the 24,000-mile circumference of the Earth in about 90 minutes or 1.5 hours. That's why it needn't take more than 45 minutes for a satellite or nuclear warhead to go halfway around the globe. The time is about the same for an altitude of 100 miles or 200 miles. If the satellite moves faster than 5 miles per second, it will leave the circular orbit and head farther out into space. At about 7 miles per second, it will not return, but will curve away from the Earth and head into a large orbit around the Sun. It will have plenty of velocity to reach the Moon. The higher velocity is called the Earth escape velocity. To escape the pull of the Sun takes a higher velocity, a solar escape velocity of about 26 miles per second. I think I won't read all of this to you, but you should read it to yourself. It's interesting. And I'm going to go on to the next thing. So hopefully you could see that the most important factor for keeping something in orbit is its speed. And we can calculate what the minimum speed is for a satellite at the Earth's surface. And of course, it would be a little bit different further up, but not that much different. And we can calculate the period of this orbit. Okay, so this is a review of circular motion, because by Newton's second law, the net force, which is the gravitational force, is the only force acting on this satellite. is equal to ma or mv squared over r for a circular orbit. Set those equal, the masses cancel out, v equals square root of gr. Now this is assuming that you can say the force of gravity is little mg. This is only true when you're at the surface of Earth, right? So we know that sometimes we're going to have to use the universal law of gravitation here instead. But this is a simpler problem, and we can calculate that velocity. It turns out it's 8 kilometers per second, and you need to know that for the Hewitt worksheets because it will ask what happens at 8 kilometers per second or above 8 kilometers per second. The second question says, what is the period of this orbit? And you can use velocity equals circumference divided by period, solve for period, and you get about 85 minutes, or as Muller said, about 90 minutes to circle the globe. You might be wondering where that constant big G came from, and actually Newton didn't know that constant when he wrote the universal law of gravitation. He just knew there was some constant there, but he didn't know what it was, and it was Mr. Cavendish who did an experiment to determine that constant. Interesting experiment with a torsional pendulum, where these masses were attracted just slightly by their gravitational attraction. It caused a slight twisting of this wire, which had a mirror on it, and the light reflected to a slightly different place on this ruler, and he was able to calculate what that gravitational attraction was. I'm going to show you this problem. I want you to think about it, and then I'm going to show you the answer, and same for the following ones. So pause your video now. Okay, so when you replace one of the masses with 2 times that mass and replace the distance with 3 times the distance, you end up getting, I wrote it down here, the new force is equal to 2 over 3 squared, the old force, because the distance is squared, and so you get 2/9. So the answer is C. Here's your next question. Pause the video. If the astronaut is at the top of a ladder trying to experience weightlessness because there's no gravity up there, he's going to be disappointed. There's plenty of gravity at the top of a 400-kilometer high ladder. If he lets go of a screwdriver, it will fall. How can he experience if he wants the screwdriver to float when he drops it, how can he see that? He just needs to be in free fall himself, like an astronaut would be on the space station. So then if he was in the space station and he dropped the screwdriver, he and the screwdriver would both be falling, and he would feel weightless. So until now, we've talked about mass as inertia, something that resists changes in its motion. This is a new definition of mass, gravitational mass, and it wasn't obvious that they were the same thing. So Einstein postulated that they were the same thing, and experiments have shown that they are. Here's a reading from the book about it. Read this and then answer the next question. Okay, here's the question, and pause your video. All right, and the answer is C, or 3, sorry, 3. That's the only one that's not a gravitational type mass, depending on the attraction of gravity. It's option 3 is depending on the inertial mass of the object. Here's your next question. Now pause the video and do this question. Okay, so when it talks about the centripetal force on each satellite, it's talking about the gravitational force between the satellite and the Earth. So, when it talks about a ratio, it's talking about a fraction. So you have you can write an expression for the force acting on satellite A, the force acting on satellite B in terms of satellite A, and then you can write their ratio, and that the answer is 1/4. All right, here's your next question. Pause the video. This is asking for a ratio of tangential speeds. Here's the solution. You can pause your video and take a look at this. It's similar to the previous one. Again, a ratio means a fraction. All right, here's your next question. Pause the video and read the question. Okay, hopefully you can tell by now that the ball's acceleration would be approximately g, because even though it's slightly higher than the surface of the Earth, basically it's close to 9.8, even when you get a few hundred miles out from the surface of the Earth. Okay, last problem. Try it yourself and pause the video. Okay, here's my solution. Check it over yourself. And that's the end. Good luck, and I'll see you next time.